Today we're going to be introduced to confidence intervals. So here's the roadmap for today. First, we're just going to do a brief overview of inferential statistics. And we've been trying to do some inferential statistics so far, but there have been a couple of problems we keep running into. And we've so far just like fudged it. But we're really going to address some of those problems head on, and we're going to come up with two solutions. One of those solutions is the confidence interval. And we're going to talk about confidence intervals when the sigma, the population standard deviation, is known, and when sigma is unknown, right? And so those are the two situations we're going to be focused on. Okay, so let's go over inferential statistics. We know the big picture idea. There's some population represented by big X, that their data is represented by big X, and we wish we could know this population. But we don't, right? But instead, what we can know is little samples. We could know that, but the problem is samples are biased. Whenever we have samples and we summarize them using these mathematical summaries, we call them statistics. And just to give you an example of some statistics, there are things like, X bar or S. Those are all statistics. What we really would like to do is use these samples to understand something about the population. And statistics, the field, is about using these statistics to estimate parameters. And to give you ideas of parameters, there are things like the mu or sigma, right? So that's our whole goal. But here, we realize in order to jump from things like X bar and S to mu and sigma, we're going to need more than just wishful thinking. And that's where the sampling distributions come in. And so here, when we talk about sampling distribution, often we're talking about some sort of statistic. And when we talk about sampling distribution of the mean, we're talking about a whole bunch of X bars. Here we have a whole bunch of X's. Here we have a whole bunch of X bars, and that's the distribution. And when we summarize these statistics in the sampling distribution, we call them expected values. So it's not just mu, it's mu sub X bar. It's not just sigma, it's sigma sub X bar. So what we really want to do is go from this to understand this. But what we have learned so far is how to see the relationship between parameters and expected values. So we know that these things have a relationship to each other. And from doing that, we could then make this jump. So it's sort of like we use this to say something about this, right? Okay, there's two problems with this picture. Although it seems rosy, there's still two sort of nagging questions. We've looked at them a little bit before, but we really need to solve this more rigorously than we have before. One question is this: what happens when we don't know what the population looks like? Of course, we could use the central limit theorem when we know mu and standard and sigma from the population, right? But what if we don't know mu? What if we don't know sigma, right? Then what happens? Also, how do we know whether a sample is sufficiently unlikely? Because remember, the whole point of the sampling distributions is for us to take sampling distributions from a known population and compare it to a sample from an unknown population. If this sample doesn't match this sampling distribution enough, if it's very unlikely to have come from this sampling distribution, we could say, this is probably not the population that this sample came from. But how do we know when it's sufficiently weird, right? Well, to answer these two questions, there's going to be two solutions. And sort of, you could sort of think of it as this one. This first question, roughly, I mean, they both actually are answered in each of these, but roughly, this one sort of goes along better with that one, and this one sort of goes along better with that one, right? And so the two solutions are these. One is confidence interval. And when we talk about confidence interval, here's what we're doing. We're going to figure out where mu might be from the sample. So we're going to try to figure out the population mu from the sample. And that's what happens, that's what we do when we don't know what the population looks like. We try to figure it out from the sample. Hypothesis testing actually takes another view. In hypothesis testing, we come up with a hypothesis for what the population is like. So hypothesize a population mu first, right? So in this case, we're saying we're just going to pull from something and figure out, and not even figure out, we're just going to pick a potential population mu. And then we're going to test how weird the sample is. So we're going to come up with a number to tell us this is how weird the sample is. And then we're going to decide, is that weirdness weird enough, right? And so that's going to be hypothesis testing. But we're going to focus here on confidence intervals. Okay, so when we talk about confidence intervals, we need to know, okay, let's get an inventory of what we know so far. And basically, that's asking the question, which parameters are known or given to us, right? So what happens when we don't know what the population looks like? Well, we may not know what the population looks like because we don't know anything about the population, or we know only a little bit about the population. So this is the case where we know a little. Know a little. So here we don't know mu, but we do know sigma, right? So for some reason we have some partial information, right? And so that really helps us out. Here we know nothing. So here nothing is helping us out. We don't know mu, and we're trying to figure it out. But we don't know sigma either, right? So it's like nothing is helping us out, and we have to pull ourselves up from our own bootstraps, right? And so these are the two situations that we're going to talk about. Okay, so here's the goal of the confidence interval. The basic idea of the confidence interval is going to be this. We're going to try to figure out where mu might be. Okay? But we do know x bar. We know everything about the sample. We don't know about the population. But in this case, I'm going to show you what happens when we already know sigma. So we have a leg up. We know sigma. So life is a little bit easier for us today. Okay. So here's the thing. We don't know what the population looks like. So we can't draw it normal or skewed or anything. We have no idea what the population looks like. And we have no idea what the population mu is. But we, for some reason, know sigma. Sigma is given to us. I don't know why. From there, can we construct an SDOM? Well, we sort of can, right? Like, given that n is sufficiently large, we could assume that it's normal. We have no idea what mu is, and we don't know what mu sub x bar is. We don't know it at all. But we can figure out sigma sub x bar. We could figure out the standard error because we have sigma, and we could divide that by the square root of n. So we have a little bit of information about the SDOM. Here's what we do in confidence intervals. First, assume that the x bar is mu sub x bar, right? So whatever your sample x bar is, we're going to put that here. We're going to assume it. Here's why. Because we always assume one thing to figure out the other. So here we're going to assume things about the x bar to figure out mu. In hypothesis testing, we're going to assume some things about the population to figure out how weird x bar is. All right. So here, because we know that the SDOM tends to be normal given a sufficiently large n, what we know is that we could find out with reasonable confidence what some of these borders, what some significant borders are. For instance, let's say we are one standard deviation away. So this is raw score, and this is z-score. So we know at one standard deviation away, this space right here, we know that that is 68% of our SDOM, right? And let's think about what this might mean. When we get these borders, right? When we get these borders, what we might end up saying is that these are the borders in which 68% of our values will fall in the SDOM. And here's what we could say. We could also say that there is a 68% chance that our population mu will fall in that zone. 68% chance. So that is a 68% confidence interval. But 68%, yeah, it's higher than half, but it's not that high, right? But here's the thing. We could have a really high confidence interval. We could have a 95% confidence interval, or we could have a 99% confidence interval, right? And so that's what we can do. We can have, here's my x bar, right? Here's 0. But what we can do is figure out these borders such that we are now sure that 95% of the time, 95% chance of having our population mean fall in this interval, right? We can know that. And so that is called a confidence interval, and that's pretty high confidence. And you could even go up to 99%, right? And we could easily figure out these borders. Here's how. Because we could easily figure out the border, we could figure out what these z-scores are, right? And this is what we call a two-tailed confidence interval. Because even though this middle part is 95%, that doesn't mean this part is 5% and that part is 5%, or else you'll have 105%, right? So that means this part is 0.025, so 2.5%, and this part is 0.025. And those are the only parts where we're not sure. That might be, so there is a small chance that the population mean will fall somewhere out here, but it's a very small chance, right? We're trying to reduce it as much as possible. So let's think about how we could find this z-score out here. Well, we could use our tables in the back of the book, right? So our z-tables. And we could look up, and usually z-tables will give you like one side, right? So we could look up 0.025 and look at the z-score, right? Or we could do it on our Excel. So instead of using norms dist, right? Norms dist will give you the proportion of the distribution. We're going to put in norms inv because it's the inverse. And here we want to put in the probability. Now this is going to be my probability. I got rid of my Excel real quick, excuse me. Okay, so I'm going to put in this probability, 0.025. And we get negative 1.96. I'm going to round it to 6. So this value here is negative 1.96. And because the normal distribution is symmetric, we know that this part is also 1.96, but now positive instead of negative. So we know our our z values on the end, right? And we want to know, okay, so if we know these z values, what's our raw score here? Tell me what this value is. And also, tell me what that value is. Well, the z-score tells you how many standard errors away you are, right? So how many jumps away. And each jump is worth that much, right? And so we're away 1.96 of these jumps, right? So we're going to multiply this by this and then either subtract it from x or add it to x, right? So step two in finding confidence intervals is, so let's say you want to find a 95% confidence interval. Find the z-scores, right? Find the z-scores. And remember, this is all in the case where you know sigma, right? And then step 3, I'll put step 3 in blue so that it's special. Step 3 is this. Now you want to actually find the actual scores. It's the finding of the scores. And so that's going to be x bar plus or minus. One time you're going to do it plus, one time you're going to do it minus, plus the z-score times your standard error, right? That's what you're going to do. And we know what the standard error is. And so I'm going to rewrite this to be x bar plus or minus the z-score times sigma over the square root of n. And when we do that, we could find these confidence intervals. And once you have this confidence interval, then you know that there, with 95% confidence, that your real mean, the population mean, will fall in this interval between these two numbers. Okay. Now, the 95% is actually called the capture rate. Capture rate, right? And so that's like 95%, 99%, right? Whatever. What would the confidence interval be for 100%? It would go from negative infinity to infinity, because remember, that's how far the normal distribution goes. But the capture rate is this: the proportion of random samples, for which this CI, for which this interval captures mu, right? So let's imagine taking a whole bunch of random samples, right? It's going to be that 95% of the time, those random samples entail mu. They somehow overlap with mu, right? So that's what we mean by a 95% capture rate. All right.